Now, practically in roulette wheel selection, what happens is that a fitter individual gets selected too many times practically. So it's the roulette wheel selection. Which is actually practical. So practically what happens is that, like in human society, there are a few stars and everybody wants to be with the stars. So if you do not apply any constraint whatsoever, the stars will get virtually every single fan and they'll mate infinite times, and all the others will be pretty much done and dusted. So nobody would get anyone. So the same thing happens in these synthetic populations as well. So practically, this is what happens. So let me write down, these are the fitness values. So 0.1, so that's extremely good. 0.8, 0.7, 0.6, and 0. Let us say 3 and 0.9. So you see that this is significantly better than others. Initially, that's exactly what happens, because whichever problem you take, neural network, all of them are random neural networks. One of them may be still having some good features, most of them are random. So most of the neural networks are bad, and therefore only one or maybe two in a large population of 100 neural networks may actually be good. Traveling salesman problem, most of the cycles will be illogical random. Only one or two may be reasonably still okay. So in any randomly generated population, the good individuals are extremely small as compared to all others, and stochastically only one, maximum two get selected. Now you convert them into the probability of selection, and this time let me give you. So first I need to invert this up so that low value is better. So the maximum is 0.9. So I say 0.9 minus, or let's say just larger than 0.9, minus the fitness of the individual. So max fitness minus 0.1 fitness of xi, and because it's not a probability, let's call as the expectation of being selected. So 0.9 minus 0.1 is 0.8, 0.1, 0.9. So this has highest probability of getting selected because it's rank 1 and all the others are small. Now so this is expectation of selection. And now I can calculate the probability. So it's 0.8 divided by the sum of all this, 0.1 divided by sum of all this, and so on, 0 divided by the sum of all this. So what turns out that this number will be extremely large, and as compared to all others, it will be extremely large. So only this individual will get selected. In fact, the problem is weird because this individual will not even get a partner to mate, because it will have to mate with itself, because at least the partner needs to get selected. So it will mate with itself and produce its offspring with, of course, the genes from parents. Both of them will be exactly the same. So the child will also be exactly the same. So virtually this individual will give birth to itself with some errors, and that's bad because one individual is dominating. So we had an entire population, but it's become a one-man show. So we'd like to solve this problem. This is currently called as fitness-based scaling, where expectation is directly proportional to fitness. Fitness higher is better, or expectation is inversely proportional to cost. Now I did not do 1 upon here because there are two ways you can take inverse. Either you subtract by something, that's the additive inverse, or you do 1 upon, that's the multiplicative inverse. So my inverse was the subtractive or the additive inverse. So this is where I inverted it up. So it's inverse of cost. There's a specific word scaling over here. So scaling is what converts fitness to expectation of being selected. Now this scaling is problematic. This scaling is absolutely problematic because one individual steals the show, one individual gets selected. So instead we use another term and we try to say that the fittest individual will not get selected all the time, and this is called as a rank-based scaling. So again, I have my individual x1, x2, x3, x4, x5 with fitness. So this is individual. It's actually cost, but then I'll write it as fitness. It's cost. And here I'll say the rank. So rank-based scaling, I have expectation is inversely proportional to rank. So this is the best individual, rank 1. The next best individual is this, rank 2. The next best individual is 3, 4, 5, and 6. Now I'll invert it up. Expectation so again I'll do additive inverse. So expectation will be n plus 1 minus rank. So lower rank, better individuals mean high expectation. So 7 minus 1 is 6. And the probability is 6 divided by sum, 2 divided by sum, 3 divided by sum, 4 divided by sum, 5 divided by sum, 1 divided by sum, where n is 21. So this is what's called as a rank-based scaling. Now, rank-based scaling is the solution that one individual does not get selected multiple times, but wallet wheel selection still has the same problem, because even now if you look at it, this individual is significantly better than all others. So ideally in a wallet wheel selection, this individual gets selected multiple times. And because this individual gets selected multiple times, we need to do about it. So summarizing, we started off with the top selection strategy. It had a problem that the weaker individuals were not getting selected. I needed some way that there should be some chance that they get selected. So I use a wallet wheel strategy. The wallet wheel strategy also has a problem that the best individual gets selected multiple times. It gets reduced with a rank-based scaling, but still they get selected multiple times. And therefore I use my last and final, and the one that I actually use, selection strategy. And this is called as a universal stochastic sampling. So again, let's take a roulette wheel, and this time let's take these individuals. So 6 by n, 2 by n, 3 by n, 4 by n, 5 by n, 1 by n. So let's take these ones and see how do they actually come out in the individual. So let's say this is 6 by n. So this is x1, this is x2, this becomes x3, this becomes x4, this becomes x5, and this becomes x6. Where it will not be completely correct because I drew it randomly. So this was 6 by 21, and then 2, 3, 4, 5, 1. Okay, it's completely wrong. And so on. Now, instead of taking 1 selectors, I take an n selectors. So let's say 4 individuals were to be selected. I take equally spaced 4 selectors. So let's take 1 over here. Now I'll have to go 90 degrees. So the second one will be here. The third one will probably be here. And the fourth one will probably be here. And of course, I rotate either the selectors or the board. And actual roulette wheel, you select the board, but then you can also rotate the selectors. So that's a rotation. And the individuals which it's pointing to, like in this case, it will select x1, x2, x3, and x5. So the 4 individuals that get selected are the ones that will get selected. In terms of program, the easiest that you can think of, so let's write this thing down over here. So this is x1, x2, x3, x4, x5, and x6. And this is some kind of a probability. So let's say 5 by 20, 4 by 20, whatever. So let me give in numbers instead. Let's say this is 0.3, 0.2, 0.15, 0.12. Point 0.3, and I converted to exactly the same range, 0.2, 0.225, 0.5265, 0.65 to 0.77, 0.77 and 0.9721. Now I have 4 selectors, so let's place the first selector randomly. So that's the second selector, that's a third selector, and that's a fourth selector. Let's place this one at 0.7. Now, the distance between the selectors will be the entire range 1 divided by the number of selectors, which is equal to 0.25. So the second selector will be at 0.7 plus 0.25. The third selector will be at 0.7 plus 2 times this, 0.5. The third selector will be 0.7 plus 0.75. And because my entire range can only go from 0 to 1, I will say a mod of 1. So that's mod 1, that's mod 1, that's mod 1. So let's solve this thing up over here, mod 1. So this will turn out to be 0.7 itself. So this is 0.95 mod 1. It's decimal mod, so anything greater than 1 is the excess gets out. So that's 1.2 mod 1, and this is so this is of course 0.7. This becomes 0.95. This becomes 0.2, and this becomes 0.45. So I need to select 0.7. I'll select it from this range, 0.2. So that's the one which is getting selected. So similarly 0.95, it's within this range. Binary search 0.2, it's boundary line case, and 0.45. So 2, 3, 4, 5 get selected. But then there's a problem, because let's talk about the complexity now. So scaling is, I need to sort it up, so it's n log n. You'll get the rank only when you sort them up. So after that it's O of n, so the sorting requires n log n time. So selection of one individual So it's a binary search, so it's log n, which means selection of k individuals. And k is always of the order of n, because I don't select one individual, two individual. I select 30% of the population that will undergo this fantastic breeding, 100% of the population, 90% of the population, 70% of the population. So it's basically n log n. Now, for this one, I cannot do anything, but for this one, there is actually a trick. I can actually do this in on times, and what do I do is, these are all in a sorted order. So first I find out 0.7, where does it belong to? I do a binary search, so it belongs to over here. Now I go to all the individuals, I see 0.77 to 0.97. Does it come in this range? Yes, it comes in this range. So I select this and I say this is selected. Now 0.2, it does not come over here. Then I go here, it does come over here. So that becomes 3. Now I say 0.45. Okay, we selected the other one. So 0.2, I go here. So yes, there it is. So that's 3. And then I say 0.45, 0.4544. So I just do a binary search for the starting point, and then I go 1, 2, 3, 4, 5. So it's log n plus n. I go 1, 2, 3, 4, 5. By the time I finish all the individuals here, this one would have been gone. So I've got 2 pointers that go level by level. The first one on the individual, on the population, and the second one on the selectors. The first counter goes here, the second counter goes here, and they both travel simultaneously, synchronizing each other. So whenever I select an individual, I increment this, and I select an individual or not, I always increment this. So you travel once over here, once over here. So n log n for scaling, I cannot do anything about it. Then log n for a binary search for getting this, then a traversal of n over here and a traversal of k over here. The problem is, of course, that the limiting factor is n log n, and it'll still be there. So that's the stochastic universal sampling. And let me give you another variety of it. It's called as a tournament selection. So let's say that's my individual x1, x2, x3, x4, x5, x6, and these are some probabilities of getting selected. Okay, so now what I do is I do it for one individual and I'll repeat it a few times. So I select random individuals, random. So my random individuals are x1, x2, x3, and x5 with probabilities as 0.1, 0.2, 0.11, and 0.25. Now I say, let us organize a championship between x1 to x5. One, two, three, five. So now the championship that I'll organize is, now if I just organize a championship, the best individual, which is x5 over here, will get selected and it'll be the winner. But I need this stochasticity thing. There should be some chance that x1, x2, x3 can also win, because that's my strategy too. That's my strategy, that the weaker individual should also have some chance of getting selected. So let's sort the individual. In terms of, it's actually fitness, but as of now I've taken probabilities, so let's work with probability. So it's x5, x2, x3, and x1. 0.25, 0.2, 0.11, and 0.1. Remember, currently higher the better, because it's fitness, it's probabilities, higher the better. Now I make these two individuals play a match with probability P best wins, and with probability 1 minus P best loses. So I take a random number and I say, is it less than P, where P could be 0.6, 0.7. It could also be based on the difference in fitness of the two individuals. But currently, let's take it as a constant 0.6, 0.7. And let's say that x1, x2 wins. So it's miracle. x5 would have won most of the times, but it's a miracle that x2 has won. That's what happens in any tournament, that many times you don't watch a match. It's India versus Bangladesh cricket tournament. Of course, India will win, but suddenly you say that let's see whether India won or not, and oops, it loses. So sometimes weaker teams also wins. So x2 wins. Now, if the fitter individual wins, then it's declared as a winner of the championship. If weaker individual wins, then it's not normal, and therefore now the winner has to play another match from the next one, x3. So now it's x2 versus x3. And because it's x2 versus x3, this time let us say the normal thing happens, x2 wins. The moment the fitter individual wins, it's declared as the selected individual winner of the championship. It's regarded as the winner and it gets to take the title. If fitter individual would have lost, it was an absolutely different thing. So currently it's the fitter individual has won, so it's x2 wins and x2 gets returned. Let's do another simulation, and so this time x5 versus x2, x2 wins, miracle, weaker individual wins. x2 versus x3, x3 wins, miracle, x3 is not supposed to win. x3 versus x1, miracle, x1 wins. So the one now x1 cannot play any other match, so x1 is declared as a winner. So now you see the chances of x5 getting selected are actually pretty high, which is P. The chances that x2 wins is that it must win the first match between x5 and x2. So P is x5 wins, 1 minus P is x2 wins, and it must win the next match, x2 versus x3. The chances that x3 gets selected is, first x21 must win in both these matches, then x3 must win both these matches. So the weaker should win, then x3 must win from x1, and similarly x1. So x2 should win here, x3 should win here, and x1 should win here. So that's extremely high and that's extremely low. So mostly x1 will not get selected because it's bad. And the number of individuals here is S, which is called as a tournament size. So this is called as a tournament size. If you take the size of the tournament as extremely large, then mostly the same fittest individual will get selected multiple times. If you take the tournament size too small, the best individual may not even get a tournament to participate and it will not get selected any number of times, the same trade-off. And for selecting K individuals, K tournaments are played. So even in terms of complexity, now you don't need to calculate the fitness value. Now you don't need to calculate the expectation value. So no expectation values need to be calculated. It can directly work on fitness values. So the complexity turns out to be, for one tournament, so I select S individuals. So S plus maximum they can be S matches between this and this, this and this, this and this. So S. So for K tournaments, and I'll always select 70% population, 80% population. So K is of the order of N. Now S is normally a constant. So that's the only algorithm where the complexity turns out to be O of N. So everywhere it's O of N log N. This is the only one where it turns out to be O of N. And that's another advantage of this. So n log n becomes O of n. But then as you know that log n is extremely small practically, and because it's extremely small practically, we will not be considering this as a great advantage or a great limitation of the universal stochastic selection. And because of that, it's good enough to get selected.